Okay, everybody, welcome to the School of Physical Sciences and our event. We're very excited to be hosting this event live from CERN, which is the world's largest particle accelerator. What I'm going to do to kick this off is introduce our two main panelists, Professor Jonathan Feng and Savannah Shively. Savannah is actually at CERN, deep underground right now, and so at some point she's going to turn her camera on and it's going to be an interesting view from that part. Oh, there we go. Okay, so here we're going to go. So let me introduce our panelists. Let me start with Jonathan Feng. Professor Jonathan Feng earned his undergraduate degree in physics from Harvard University, his MA in mathematics from Cambridge University, and a PhD in physics from Stanford University. He joined the faculty at UC Irvine in 2001 and recently was named Distinguished Professor of Physics and Astronomy. Jonathan studies theoretical particle physics, astroparticle physics, and cosmology. He's a fellow of the American Physical Society, and his work on understanding the universe at both the smallest and largest length scales has been recognized by the Sloan Foundation, the Simons Foundation, and Guggenheim Fellowships. He's a frequent speaker at conferences and institutions around the world. His research and interviews have been featured in a diverse range of publication, including Science, Nature, the Washington Post, and USA Today. Next, we have Savannah. Hi, Savannah. Savannah Shively is currently a graduate student at UCI who works with Professor Feng. She came to UCI as a transfer student from Irvine Valley College, and got her undergraduate degree in physics in 2018. She then joined the physics department as a PhD student right away, and we were thrilled that she decided to stay here and do her PhD. In February 2020, with the support of two UCI alumni, she traveled to Europe so that she could work at CERN on this experiment FASER that you're going to hear about today. And she's there right now, and she's going to tell us more about her work and what she's doing there in a few minutes. But before we do that, I'm going to hand the mic over to Professor Feng, and he's going to tell us a bit about CERN and this fantastic experiment FASER that he has spearheaded. In the meantime, let me just say that you have a question and answer box you should see there on your Zoom, and you are free to ask questions in that box. Just type them in, and I'll be monitoring them in real time, and we will try our best to get them all answered. So anytime you have a question, just that's the way to do it. And we're gonna be taking those questions live throughout. So thanks very much. And with that, Jonathan, I'll hand it to you.
Okay, well, thank you very much, James. We're thrilled to be taking part in this event live from CERN. What we're gonna do now is I'll just show a few slides to hopefully orient everyone as to where Savannah will be talking to you from and what the CERN and the LHC are, and then she'll take it over from there. So to start at sort of the biggest scale, of course, you all know where Geneva is, and CERN is, as Dean Bullock said, the largest particle collider on the planet at the moment, and it's in Geneva. And so this is the collider. So in this ring are protons that are being accelerated. One beam goes clockwise, one goes counterclockwise, and then they collide. And from that, we try to learn what we can about what makes up the universe, the fundamental building blocks, and really, the origins and the fate of the universe. Just to give you some sense of scale, I hope you can see here, this is the Geneva airport. And so this is Lake Geneva over here. And so this is really a monumental scientific instrument. It's 27 kilometers long. It's 100 meters underground. So, you don't see it from space like this. It's just drawn on top, but it's actually 300 feet underground. And it's accelerating two counter-rotating beams of protons, as I said, to incredible energies. They're going at 99.999999% of the speed of light, plus or minus a 9. I'm not completely sure I got all the digits right, but lots of 9s. So this is CERN, and then this is the LHC, this ring here, the Large Hadron Collider. And so then now let me focus down on this part of this big complex. So if you zoom in, what you see is LHC, just a portion of it. So the LHC is this thin blue line that's sort of going across the diagram here. And the FASER experiment is basically along that tunnel, and we'll be looking for new particles. So FASER is the forward search experiment, and it was proposed by a number of us at UC Irvine in 2017. Construction started in 2019, just 2 years later, and it was completed just a few months ago this year. So that detector, FASER, is down there, and Savannah will show you it and tell you all about it. But the LHC right now, which is the source of these proton collisions, is currently shut down for upgrades. So there's no protons running down these beam lines right now, but it will turn on again in 2022. And we're eagerly awaiting those proton collisions to start so we can begin taking data here in FASER. Now let me sort of zoom in one last time into this particular region here so you can kind of feel for what's going on. So what are we actually looking for? So in a sort of schematic form, this is this giant detector called Atlas, and we have UCI collaborators there as well. That is where the protons are sort of induced to collide with each other. And then what we're hoping for is to see particles that come in the forward direction. So FASER is called the forward search experiment. Forward means basically straight along the beam line. And so particles will come from Atlas 480 meters down the beam line, eventually going into the concrete and the rock in the side tunnel, and then showing up here at FASER. And as you can see in this diagram, what we're trying to find are primarily two things. One are neutrinos. So neutrinos, of course, are known particles. They were discovered by Fred Reines, founding Dean of Physical Sciences at UCI. And for that, he won the Nobel Prize in 1995. So these are known particles, but they have a lot of mysteries that we're trying to solve. And in particular, FASER can bring to the table the fact that we're looking for the highest energy neutrinos ever detected. So Reines's detection was, a watershed moment, but it detected the very, very low energies. We're actually looking at energies that are 1 million times higher now. And we're hoping that we'll sort of understand neutrino properties better and maybe uncover some new mysteries neutrinos have. Second thing we're doing is looking for other particles that are possibly being created there. And these include what are called dark photons, or more generally portal particles. And Savannah can tell you more, but basically the idea is shown here in this little pie chart. As many of you might know, the atoms of the periodic table only make up about 5% of the universe. And we know that with increasing precision these days, the other 95% of the universe is really a complete mystery. And in particular, there's a chunk of it called dark matter, which holds our galaxy together, and we just have no idea what it is. And so this is one of the great mysteries in fundamental science right now. And we're hoping that FASER can tell us a bit about that. In particular, we're detecting what are called portal particles that sort of may communicate between us, atoms, and the dark matter, and which sort of give us a view or a portal on the dark sector. So those are two sort of parts of the physics motivation, the scientific motivation for this experiment. All right, so that's just some overview. As you see here, there's this LHC tunnel that goes along here, and there's a side tunnel here, and FASER is sort of in this side tunnel here. And we're just really happy that we have Savannah now, who's actually located 100 meters underground at that location, and so can show you FASER. So let me hand it over to Savannah.
Thanks, Jonathan. I think I'll show them the tunnel first. So I'm just going to climb up these safety stairs here, and hopefully the connection stays okay. So here you can see the LHC itself, which was what Jonathan was talking about. So you can see far in the distance that it slowly curves away, so you can get a scale of how big this thing is. And similarly, it goes off in the other direction. So we're tangent to this circle. And over there, you can see where FASER is located in TI-12. I'm going to carefully climb back down again. Okay, so yeah, thanks. So I'm gonna switch it around. So now we're going into the tunnel where so the main detector is this apparatus that you see right up front. So the particles that come in from Atlas come in from this direction. So you can imagine them arriving this way and traveling all the way through the detector and passing through all of our detectors until we end. And I'll walk through what each of those means. So you might hear this kind of whirring noise. That's actually our cooler, which is this device over here. So this keeps our trackers from overheating and functioning within the parameters that they should be working on. So if we look at things right here, so we actually, the tunnel is excavated to accommodate the detector, and the particles that come in the beamline from, sorry, let me start again. So if you think of Atlas as kind of like a soup can, it has all of these detectors on the label of the soup can that are suited to detecting these massive particles that come off from stuff smashing together inside. But they have to let in the protons in somewhere, right? Which means that they have a blind spot along the axis of this soup can where we don't really know, we don't have any detectors feeling out what's coming off in that direction. So that's what FASER is perfectly situated to do. So off of that soup can axis, the particles come in. If there's any kind of noisy particles, that's what this first simulator station takes care of. And if we have a dark photon, it will propagate through and hopefully decay into this decay volume here, which is a magnet. And it should decay into an electron-positron pair, which, because it's going so fast, they will be very close together. So we use this magnet to separate it further, and we have 3 of these. So we get separated all along this path. So these electron-positron pairs then go through these tracker modules. So this is something that I've actually been able to work on. So thanks to Nancy and Corwin Evans, especially because without them, I wouldn't have been able to get my hands on helping set up this detector. So thank you very much. So these trackers.
Savannah, can you hear me, Savannah?
Yes.
Maybe just speak a little slower. The sound is a little broken up, and so
Okay,
people are noting that it's a little hard to hear.
All right. So electron positrons travel through these detectors, these tracker modules, and they split up further. These magnets, tracker. Now, what these trackers do is that every tracker plane that it passes through is 1 coordinate. So every time a particle passes through, we pick up where it is. And part of our efforts nowadays are being able to reconstruct the path that a particle takes all the way through the detector until it ends up over here in the calorimeter. And the calorimeter is here, so when particles get to it, we can have some idea of how much energy they have. Yeah, so.
Oh, great. Hey, Savannah, thanks so much for this. I think something that might be helpful, just because the connection, unfortunately, is not great. Jonathan, do you think you might be able to summarize just a couple of the things she said, almost as like a translation for those of us who can't hear very well? And there are a few comments too and questions that maybe the 2 of you can try to help cover. But Jonathan, maybe you could try to give just a brief summary of what she just explained with that visual.
Sure. Sure. So yeah, Savannah said a number of interesting things. One is she was saying that the traditional particle detectors are, you can think of them as like soup cans. So they're sort of cylindrical and they have a lot of components along where the label is. But then they have sort of a hole down the center, which is where the protons come in and collide. And the thing is that if your particle you're trying to find comes straight back down the line where the beams came in, then you're just going to miss them because the soup can is sort of instrumented on the label, but not around the ends. And so this FASER detector is designed to catch all those. And so that's sort of its unique advantage. And then Savannah pointed out, actually the connection looks a little bit better now, maybe. So let's see if it goes back. But then Savannah pointed out that basically, if you see behind her, the particles are coming toward Savannah, sort of out of this floor toward her, right? And so then we have various pieces of the detector that are designed to basically catch those particles and make sure we've recorded them. In the far back, there's a cooler, which is basically just like an air conditioner or a chiller for the water, which keeps the detector from overheating. And then there's electronics racks back there, tons of data pours out of this thing. And so we have to, of course, record it and send it to some disk or, to the cloud or somewhere. And then Savannah went through and showed each of the components of the detector. So in particular, there's magnets, these big blue cylinders there, which bend the particles, help us to figure out how fast they're going and what they are. And then, yeah, as we move along here, there's scintillators, which basically allow us to record when a charged particle is passed through. That's what she's pointing to there. And then at the very end there is what's called the calorimeter, which is basically to sort of figure out how much energy is being deposited. So like an electron will just plow into that last component. And by figuring out how big the shower is that it creates, we can determine how much energy there was. And the things we're looking for are extremely high energy. And so that would help us to distinguish the signal, the important part that we're looking for from the background.
And we have a question here that I think maybe Savannah can answer. It's a simple one. It's just, how much time do you spend at CERN? How long have you been there, and how long, just in a typical year, how long are you there, and what are you doing when you're there? Are you building this thing? Are you analyzing the data? What's going on right now?
So I arrived in Geneva about a month before the pandemic started. So that is now almost 2 years ago. When I got here, FASER was still in what's called a commissioning phase, which means that we test the individual electronic components before assembling them in their final configuration down in the tunnel. So we went through this iterative process of testing things piece by piece before installing them into a bigger piece, and then testing the bigger piece, and then putting that bigger piece where it was finally going to go. So a lot of the time that I spent here was doing electronics testing and writing code that helped us look at some of the electronics data that was coming off of these devices to make sure that they were functioning properly. And nowadays, my focus is shifting to reconstructing data that will be arriving off of the detector once run 3 begins.
Great. Okay, that's very useful. So we have another question actually from John, which is, is there any reason to expect that these particles are going to be generated in the forward direction? Or is this just exploratory to see what's out there, as Atlas may have missed? Because again, Atlas is this sort of soup can and it's looking for stuff that flies off that way. And you all are looking for stuff that goes straight. Why are you thinking that stuff goes straight? And then why didn't people think about that before? So maybe give us that a little background.
So it's not just when considering particles, especially when you're smashing stuff together, they have a mass component and a momentum component. So when these particles smash together and rearrange themselves, you can kind of think of it like a budget. If you're making a heavier particle, you have to spend more of that energy budget going into mass. So there's not much momentum that would carry it in the forward direction. So all the heavy stuff gets picked up in an atlas, but things that are lighter in mass, like the dark photon, get created, with more of the energy budget in momentum. So these kinds of particles would be generated with lower mass but higher momentum, which pushes them in a forward direction instead of this radial direction.
Oh, that's helpful. Okay, great. Thank you. And then we have another question, which is, does the 100 meters of rock between the LHC tunnel and FASER serve any function for FASER? What's the purpose of that, or is there a purpose for that?
It kind of existed when we got here, so we're kind of taking advantage of its existence. And it serves a purpose because it catches a lot of the high energy, heavier stuff that would be considered background if it were generated at the interaction point. Because what we're looking for with the case of the dark photon is like neutrinos, which don't interact with much. They pass through all of this material without interacting with it and make it to our detector before they decay. So the intervening rock serves to catch things that we don't want to pick up in the detector. So it conveniently is the case that we have all of this infrastructure in rock, which produces noise.
Great. And now we're asking, people are asking, can you say, you said the words dark photon. What is that? And why is it interesting? Do we think they exist? What is a dark photon, and how is that different than the normal photon that makes the light that helps us see?
So a dark photon is kind of similar to a photon in that it interacts with electromagnetism. So the dark photon has mass in some theories, and it serves, basically it's what's called a boson. So a boson is a particle that dictates the forces that you're familiar with, things like the electromagnetic force, or lesser known weak force and strong forces, something else you might have heard of. So a dark photon, we're hoping, if we see it, is a portal particle that relates standard model materials to what would be the dark sector, where we would maybe hope to find dark matter. Yes. Did that cover it, I think?
I think that helps. Jonathan, did you want to add anything to that? Or?
Yeah, just to add to that. So, we are almost 100% sure there's this stuff called dark matter, but we don't know what it is. But one possibility is that it could have its own dark forces under which it interacts with itself. And so just like, electrons interact with photons and light in our visible sector, there could be sort of dark photons interacting with dark matter in the dark sector. And so that's well and good, but how do you see it? But it turns out these dark photons, they can sort of have a little bit of leakage into our sector. They can talk to us, not very strongly, but there's a little bit of small interaction that we can actually see. And so that makes these particles kind of neutrino-like, very weakly interacting. But if we do see them, they would be like our first glimpse of actually the photon that's existing in the dark sector. And so that's how it would sort of start telling us about dark matter and the dark universe.
And is this the goal here? I mean, was this what you were sort of originally thinking about when you designed and built FASER to detect these dark photons or particles like them? I mean, we have a question is this just pure science to see what comes out in the forward direction, or was that the original thing that kind of motivated you to do this in the first place?
Well, so yeah, when we wrote the first paper about this, it was actually to think about detecting dark photons, to discover dark photons. And then it sort of blew up. It turned out that once you figured out what detector would be really good for detecting dark photons, you found out that that same detector would be good for detecting dark Higgs bosons and axion-like particles and dark gauge forces. And there's a whole bunch of words that go with this. And then even more exciting, it turned out that you could actually detect neutrinos at the highest energies that people have ever created them. And so that was almost a bonus. Of course, it's a pretty big bonus because, you know, that means we're guaranteed to see something. And just as a sort of footnote, it turns out we've actually already seen 6 neutrino candidates that were produced at the LHC. This is the first time anyone has ever seen a neutrino produced at the LHC. And so we're expecting about 10,000 of these in the coming years as soon as the LHC turns on. But it's kind of an example of, you start with something small, but if it's a sort of unexplored region, other things come along for the ride. And so now there's a lot of things we're looking for.
Yeah, these. Go ahead. Sorry, Savannah. Yeah.
I wanted to interject while we're on the topic of neutrinos. So let me try to show this to you. So this little gap that you see, I'm gonna not throw my iPad on the detector, that would be bad. So this gap under here, this entire length is where the neutrino detecting portion of FASER new is going to go.
So you're waiting to install that, and then so now that you've detected, you have these candidates, maybe not enough to officially, with the rigors of sort of particle physics, declare officially that you have these detections. You have this new piece you're going to stick on, and that's going to allow you to detect many more and start doing interesting, maybe neutrino science with these incredibly high energy neutrinos. Is that what's going to happen?
Yeah, that's exactly right.
And just to clarify, we've got some questions. I think many of our alumni and people who pay attention to what's going on in the physics department are aware that there are a lot of experiments that we're involved in that are about detecting neutrinos. We have experiments at the South Pole using the ice, many other things that people have heard about. So maybe just clarified for everybody, how is this different? They're super high energy, they're coming from a collision. Talk to us a little bit more about how is this different than the other kind of neutrino physics that we are doing so much of at UCI.
Should I take this one, or would you like to go?
Go ahead, Savannah, because I know you actually worked on some of the other ones too there. So go ahead.
I used to work on Ariana. Yes, so essentially FASER is going to help boost our numbers, just getting more observations of neutrinos. That these are human-made neutrinos, which is something that's been done, but not at these levels of energy. So in most neutrino detectors that are human-made, it's usually what's called fixed target experiments, and they have so we're really taking advantage of this 13 TeV particle collider to detect these high energy neutrinos down in FASER's direction. So we're filling in some nice gaps in neutrino data. What part cut out? Did you guys
Yeah, just to fill in, because I think some of the sound was a little bit choppy. So just to fill in some of that. So Savannah was saying that we've done a lot of neutrino science at low energies, starting with the work of Rhinus and carried on with lots of really good people at UCI. This will be the very billion times higher energy, and there are things about neutrinos that will get revealed when you go to such high energies that might have been hidden at low energies. The other side, though, is that there are even higher energy ones that are being searched for at UCI through the work of Steve Barwick's group. And those actually even dwarf the LHC energies. But number one, we haven't seen those yet. And number two, they're sort of produced in a much more mysterious way because they're just coming from some astrophysical source, and we're not necessarily even sure where they're coming from. So the advantage here is that we have a very well-defined source. We know about the LHC. We've understood the LHC. We understood how protons interact when they collide. And so, we can make predictions that are a little bit more accurate. And then if we see deviations from those predictions, we might have discovered something totally new. Whereas if it's just in Ariana, this astrophysical experiment, if you see some deviation, well, maybe you just didn't understand the source of the neutrinos very well.
We have a question from a self-proclaimed non-physics major, but I think it might be a broad question. There's some confusion as to, how are these neutrinos being accelerated if they don't have charge? So I think there's some clarity, some clarification to make. Where are these neutrinos coming from originally here, say at the LHC? Like, where are the neutrinos coming from? Are they being accelerated? Why are they coming down that beam?
So the particles that are being accelerated in the LHC are packets of protons, which are charged. So these protons get accelerated to very high speed. So we're putting energy into the energy bank, boosting our budget. So once they finally smash together inside of Atlas or any of the other interaction points around the LHC, they rearrange and interact with each other and produce all sorts of particles. And among those particles can be neutrinos. So these neutrinos get their energy from this energy budget of the colliding protons. And they, because they're such low mass, that energy budget goes into their momentum. So you can have these very high energy neutrinos coming down the beamline that reach FASER.
That was very clear. So they're getting made in that collision. They're not being accelerated by the thing, but great. And then I guess the next question that Ken is asking is, okay, neutrinos are these super non-interacting particles, but you are doing this amazing feat because you're detecting them somehow. Can you tell us a little bit about how do you detect one of these neutrinos if they're so weakly interacting?
So an interesting property about neutrinos is that the rate at which they interact with matter changes depending on what that matter is and also on the energy of the neutrino itself. So one of the ways that you can catch a neutrino is the way a lot of neutrino detectors do it is by just sheer volume. So you have a lot of stuff that you can run into and you look at all of it at the same time. Or like in FASER, you set it up with ultra dense materials like tungsten. So FASER new, which is going to go in the front, in the hole that I showed you, is going to be made of mostly tungsten. And when a neutrino interacts with tungsten, which has a higher likelihood of doing so, then that causes a particle shower to follow. So we detect that shower and use that to understand the things like the energy and momentum of the neutrino.
That's amazing. So you're talking about adding to FASER now. What are the plans? So you have this sort of first FASER, and you've shown that you can probably detect neutrinos, and now you're going to add this other piece, and you're going to detect even more. What's the game plan? Like, what do you want to do? Is that the next step? Is that the final step? Do you have visions for more bigger FASER, super FASER? What's the game plan going forward here?
So we have one more tracking station to install, which is going to help us with noise and also to detect some of the particles that'll come off of FASER new. After that, that's when FASER new will be installed. And that's what's going to happen before run 3 begins sometime early mid next year. And after that, there's a possibility of FASER 2. I don't know how much we should get into that here, but that might be for like a future run. So maybe not run 3, but sometime in the future.
Great. And then
just to follow up on that. So, sorry, James.
No, go ahead.
So Savannah is talking about run 3. So that is, as we talked about, the LHC is shut off right now, which is why it's okay for people like Savannah to be in the tunnel. As soon as that thing turns on, you don't want to be anywhere down there. Run 3 is going to start in, mid, as Savannah said, early to mid 2022, so in a few months. And that'll go on for maybe 3 years. But that's by no means the end of the lifetime of the LHC. After that, there'll be a shutdown, more upgrades, and then it's envisioned to run for another decade after that. So, the LHC has been going for 10 years or so, but it's sort of, in its middle years. It's 30 years. It's by no means an old person. It's not elderly. It's got a lot of life left in it. And so the idea is possibly to make an even bigger phaser, which we're calling phaser 2, which would be bigger and take advantage of that whole more decade of running and gather possibly 100, 200 times more data even than phaser itself.
Great, thanks, Jonathan. Okay, so we have another question, which is how is UCI's effort at CERN funded? I guess it's a broader question about CERN. I don't know, Jonathan, maybe that's a question more for you. Maybe you can tell a little bit of the story of how FASER is funded, which is a tremendous story. And then more generally, it might be useful just to kind of talk about how is it that a university like UCI participates more broadly at CERN.
Yeah, sure. So CERN is, it stands for like a European Nuclear Physics Laboratory. That's CERN in French, I think. It's designed to be a place, it's called sort of a user's facility. It's a central meeting place for people from all over Europe, but now in the way the world is now, all over the world come there to use the facilities there. And so UC Irvine, for example, has had researchers at CERN for decades. So the way FASER came about is kind of interesting. Four of us at UC Irvine, 3 postdocs and myself, we came up with this idea, realized that it could actually be really interesting and quite doable. And then we sort of, sent it into the scientific literature and waited for reactions. And to make a long and arduous story short, eventually there was support among scientists. People thought it was a good idea. And then we went out and tried to get, support for funding it. One major component is CERN itself. So you see this tunnel that Savannah's sitting in, it didn't look like that when we started. It was a side tunnel filled with junk and all sorts of stuff, hadn't been used for 20 years. And, it costs a lot to prepare the tunnel, to move equipment in there and to build the thing. So CERN provides what are called host lab expenses and does a fantastic job basically hosting the experiment. And then we also got essential contributions from private foundations. So the Heising-Simons Foundation, the Simons Foundation, also JSPS in Japan, and other funding agencies have chipped in. And then also critically, some extremely generous private donors like the Evanses have helped contribute to support graduate students. It's not cheap to live in Geneva. And so moving people there so they can actually work on experiments is totally critical. And so that's kind of how it's come about, sort of a combination of a lot of sort of federal monies, but also private foundations and private donations.
Thanks, Jonathan. Yeah, it's a fascinating story. And I think Jonathan is too humble to sort of really say this forcibly, but this is really something that came out of his group and now is an international collaboration. My understanding is it's the first new experiment at CERN in many, many years. It's now one of, I think, 8 total or something. Maybe I've got that number wrong, but there's not that many experiments in the largest, most powerful particle collider in the world. And one of them was sort of born, initiated, and spearheaded, and now run, PI'd by folks at UCI. So it's something we're very proud of. And it's really cool to have Savannah there. I mean, are you expecting to be there, by the way, Savannah, for another year or two? I mean, you've been there since the pandemic. Are you going to come back and write your thesis? Are you going to stay there? Like, what's that like? And then also, what's that like? Have you enjoyed it? Is it crazy working underground a lot? Like, maybe tell us a little bit about that experience as well.
I really love living in Europe. If my family and friends were all here, then I'd probably stay here for as long as I can. My current plan is to stay here for an additional year, and then near the end of my 5th year, come back to UCI and finish out my doctorate there. And yeah, it's been great. coming into the tunnel is, I realized today too, is quite a bit more rare and special than I thought. So I've come down here a couple times to help with the installation, but ideally this whole system is self-sufficient. So once things are up and running, we're not going to be allowed to be down here at all. So the less that we have to come down, the better. So a lot of my work has been on the surface in CERN's Myron site. That's where we did a lot of the electronics testing. And that's also a very special place to be as well.
Thanks. You know, there's a few questions here that are kind of circling back to how fast things are traveling in that beam, the beam. I think people want to know, like, how fast are the neutrinos moving? How fast are those particles moving? There's a question here about Lorentz factors. So it might be worthwhile just kind of talking a little bit more. You know, what happens when you're speeding these particles up, and do we know if neutrinos are moving at the speed of light, or are they not quite moving at the speed of light? Like, maybe just sort of give that kind of little bit of background just on how fast stuff is going.
So when considering energies of the things that are traveling around the LHC, it becomes almost, how to say it, it becomes hard to describe how fast they're going because they're going that close to the speed of light. Like how you saw in Jonathan's slide, 99.99999% the speed of light. So not quite there, but pretty close. So it becomes better to quantify how fast they're going in terms of energy. And so in run 3, the LHC is supposed to, if I'm not switching the numbers around, it's 13 TeV. So 13 tera electron volts. And that's the energy that's going to be put into these protons that are smashing together. And everything that comes off of that is getting some chunk of that energy, and it's going that fast accordingly.
Can you help us understand what 13 TeV means? I've heard analogies related to sort of the kinetic energy of something we might even think about, something like a baseball. Like, do you have anything like that up top of your head that you can help us sort of understand how much energy that is in a particle that's effectively, you know, incredibly light? I don't mean to put you on the spot. I mean, it might be Jonathan might have that stuff too. If you haven't taught physics 101, you might not have that on top of your head. So
it's not quite. Yeah, it's not quite the energy of a major league fastball. Might be not far from the energy of a baseball I would throw, but you know, it's pretty amazing. It's a lot of energy when you think it's packed into a fundamental particle, right? And so I don't know, there are some things you can get off the web, like the amount of energy in the beam at the LHC is sort of like the kinetic energy of an aircraft carrier, you know, going 40 miles per hour in the water or something like that, something crazy. Of course, that's split into many different protons, but that does give you a sort of a feel of sort of macroscopic energies packed into microscopic objects. It's
incredible.
And it's a culmination of, you know, 50, 70 years of incredible work by accelerator physicists able to do this. The beam is going around, as we mentioned, 27 kilometers around, but it's all in this, you know, super cold state because the magnets have to be down at, you know, a few Kelvin. And so it's sort of the largest super cold system ever constructed. And the beams, when they actually collide, are focused down so that they'll hit each other as much as possible, focused down to something like a few microns, so a few millionths of a meter. And, you know, to get them to do that when you need them to, and then get them to go all the way around again when they haven't collided, it's a real feat. And people like Savannah and me are more users in that sense. You know, the real heroes of this are the accelerator physicists who provide that beam and that quality of sort of collisions to us. But we appreciate it.
I mean, it's amazing, right? It really is. So let me just say, we've actually gone 15 minutes over, and the number of people watching this webinar has not gone down. People are just transfixed. And so I appreciate both of you giving us this extra time. Let me just throw one or two questions at you because we've got so many people are so excited about this exciting science. Is there, so let's go back to this dark photon question. What is the signature of these dark photons? So you're finding neutrinos. What would a dark photon look like, and how can you tell the difference? Or, you know, what? Talk to us a little bit about that, if you could try to explain it briefly.
So a dark photon, like a neutrino, doesn't interact with ordinary. It doesn't like to interact with ordinary. So that's how it's able to traverse 500 meters and not interact with anything in particular. However, it has a mass, which means it has this finite lifetime, among other factors. But so this has a finite lifetime, which means that at some point it decays. And this is the case for a lot of particles detected in ATLAS. So the dark photon will decay. It's one of the primary modes of decay will be into an electron-positron pair. So this electron-positron pair will be what's detected. So our detector, the signature of having this oppositely charged pair coming through the detector. So the key will be to find these paths, which will look kind of equal and opposite, and we have to be able to trace it back to a point of origin inside that first magnet, and it has to point back towards the interaction point inside ATLAS. So that will be what a dark photon candidate looks like. So electron-positrons, the momentum points back to a point where they spat out inside of the magnet, and all that momentum has to point back towards the ATLAS interaction point.
Got it. Very interesting. So let me ask one more, which is sort of a question I have no idea. Do you either of you know how much power or electricity is used by CERN by the LHC to do this, and how and where does it get that? Where does it get that energy?
Well, okay, I don't know the numbers, but I can tell you that one of the reasons the LHC shuts down in the winter is because you know, it's a significant drain, and when power should be used to heat buildings and keep people warm, it's both not a good idea and also kind of expensive to run the LHC. So that's why there's actually a winter shutdown every year. And I think there are other funny little effects, like in the LHC, in these colliders, it's been noticed that when the TGV, the bullet train goes by, it pulls enough power out that you can actually see that effect in the collider. And so, you know, it's a pretty massive operation. But
wow. Yeah. So I'll go back with one more sort of science question, and then we can wrap it up, and we can let Savannah go and have an evening and have some rest here. But back to the neutrinos. So people have mentioned, I think much of our audience is aware, there's these three types of neutrinos we know about. We know that we have questions about what the neutrino masses are. What neutrinos are you looking for? Will you be able to inform any of those questions about neutrino oscillations, neutrino mass, stuff like that, or is the physics somewhat different here?
So I can maybe take the first stab at that. So that's actually an essential point, this idea that there are actually three types of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. Very interestingly, despite the millions of neutrinos that have been detected, about 2 handfuls of tau neutrinos have ever been seen in the history of science. Tau neutrinos are probably the least well-studied particle that we know exists. And so it turns out, because of the huge energies of the LHC, we actually get a fair number of tau neutrinos also. And so that's one area where, really nobody knows what tau neutrinos interactions are like, because, all the error bars are like, plus or minus 100% sort of things. And so we could see some interesting effect there. And in terms of the mass generation stuff, there's all sorts of, open questions about neutrinos. There's ideas that maybe the neutrinos, we know now they oscillate into each other. Electrons turn into neon neutrinos turn into electron neutrinos, etc. But there's some ideas that maybe some of these turn into a fourth neutrino. It's called a sterile neutrino, and we don't know if that's true or not. And so we could see effects like that also, which you know, we happen to be looking in a place where very few other experiments are sensitive, and so we could actually see an oscillation to a sterile neutrino, which would be evidence that there's, you know, four kinds of neutrinos, not just three.
Wow, that's amazing. So much fun and amazing science that you all are doing and leading. And let me just give Savannah here the last word. I mean, do you want to say anything about what this experience is like, what you're most excited about for your own research? You know, what's in your head right now in terms of what's motivating you and what you're excited about over the next couple of years?
Honestly, I'm very excited to just be able to share the magnitude of the science that we're doing, and to hopefully get other people also excited, because we're, you know, this could be uncovering something that breaks through in a whole new realm of physics. And it's really a privilege to be here and to have seen this project from start and basically to the end. And that's just been a really special and unique experience. And if you're out there and you're interested in science, look for these opportunities. It's not always going to be critical to your career. It's important to look into what you can get involved in and get your hands on as much as you can. That'll teach you a lot.
That's great. Nice words of wisdom there. Well, let me just say, I think I myself am inspired by what you're doing, and I'm sure a bunch of the audience is too. So thanks so much for your time. This has been real special. So, and Jonathan, you too. Any parting words?
No, Savannah said it better than I could have. So just happy to take part. Thank you very much.
Great. Hey, thanks everybody for turning up today. It's been wonderful. And until next time, bye-bye.